Okay, good afternoon, everyone. This side Shekhar Tyagi, working as an assistant professor in Computer Science and Engineering Department, IIMT College of Engineering, Greater Noida. In today's discussion, we will be having a lecture on implementing concept learning using version space graphs with the help of machine learning. So, first of all, what actually a concept learning means, we will be basically discussing it within some exemplar approach that what actually a concept learning is and how we are basically plotting the version space graphs with the help of machine learning algorithms. Uh, so moving on, what actually a concept learning is and what are its implementation, what are the algorithmic approaches, particularly like finders algorithmic approach and candidate elimination algorithm approach that we are basically going to use. So starting with concept learning, I have taken an exemplar approach that you all will be basically visible to all of you. That what kind of days, which days are basically suitable for enjoying a sports activity. We have some set of parametric values that will be deciding some on the basis of these values, we will be deciding on some sort of training examples. And these sort of training examples will be both negative examples and positive training examples. So these parametric conditions that I have taken for the evaluation purpose are sky conditions, humidity, temperature, wind, water, and forecast. So all these are attributes and we will be providing some values, and on the basis of these values, we will be basically creating some hypotheses. And in the next phase, we will be evaluating those hypotheses for obtaining some particular type of results, that what will be the particular outcomes being showcasing for negativity and positivity in the training sets, right? So moving on the next, we have what actually a task is, and a particular task is signified with a learning task, and that a hypothesis basically judges a particular type of set based on negative and training examples. And what we want to make a hypothesis about the day, right? In this particular example, we are taking up a certain type of attributes, and on the basis of these attributes, we will be basically deciding on what kind of learning task the basically will be evaluated, right? So finding the hypothesis, actually the right hypothesis function from the historical data will be of very prime use in that case. So this is our training examples that we have deployed for a particular set of values. You will be basically seeing that there are 7 types of parametric or attribute values that we have taken with. First is the sky condition, second is temperature, third is humidity, wind, water, forecast, and enjoying sports. So this is the final outcome that we basically have to yield for, right? So we have taken some values, like in the first case, we have a sky condition as sunny, temperature as warm, humidity normal, wind is strong, water is warm, forecast is same, means the previous day forecast and the current day forecast is almost similar, right? So in that condition, what we are basically yielding is a Boolean 1, right? Or we can basically represent it with an yes value, right? So here we have to define a target function, which we are basically representing in that scenario as C. Small c will be the target concept, target function. So in the first case, the target function is yielding a 1, right? So target function will be basically moving on either 0 or 1. So in the first case, all these parametric values will be evaluated and we will be having the particular result. So the first value which we are basically getting is a 1, right? Moving on the next, we are again getting a 1. In the last, we are again getting a 1, right? So in that scenario, whenever we have an attribute sunny, which we are basically termed as an important attribute, or we can say that this is the prime attribute, right? So when the prime attribute we are having is a sunny, then we are getting the result as 1, right? But in a scenario when we are having a prime attribute as rainy, right? So obviously no outside activity is being possible. So we are representing this type of training concept with a 0, right? So basically there are 2 types of algorithm that we will be discussing with one by one. And both these algorithmic approaches are based on some graphical representation, graphical implementations. And these type of graphical implementation can be imparted in 2 ways. First is the decision tree approach, and second is the version space graph approach. Although decision tree approach is a very conventional type of approach, but in the recent years, what we have been shifted from a traditional type of approach to a dynamic type of approach, and that dynamic type of approach is version space graphs, basically, right? So the prime concerns that we are basically discussing in this scenario will be the version space graph and how version space graphs are responsible for imparting two types of algorithmic structures. First is finders algorithm, and second one will be the candidate elimination algorithms. So the main requirement is that how to basically free up the memory space that is being utilized by negative type of training examples. So either in the first scenario, we will be basically ignoring them, and this type of algorithm will be finders algorithm, and in candidate elimination algorithm, we are basically removing the odd ones, that the negative training examples, right? So moving on, we are having, so the concept learning here states that for a particular training set, these are our training sets. These can be a million of training sets, just an exemplar approach. So we have here constituted about four types of, you can say, the column and row order specifying. But this data can be more abundant, right? This data can be more enlarged, more bulky data may be there. There may be data types will maybe ranging from several millions to multiple billion type of values, right? We have to process on that. So the prime thing is that we have to decide two types of things, two types of concepts. First is we have to trace down some negative training sets. We have to trace down some positive training sets, right? So that is about concept learning. So what we basically plan up for is that we just create some hypotheses. We evaluate those hypotheses with the help of a target function, that is C, right? So now the important thing is that when we are basically aiming to plot a version space graph, then how we will be basically constructing the hypothesis, how we represent the hypothesis, how we construct the hypothesis. So there are three types of values a hypothesis can represent for. First, a specific value, right? Just like a condition, water. So water is either warm, right? It can be cool as per the attributes that we are having. So these are some specific values. But there are some values which we are basically don't care about, right? Either the value of water will be anything like that, or it cannot be mainly for justifications, like it is not affecting the training sets values or the hypothesis at all. So we can basically represent it with a question mark. So this type of representation that doesn't play a significant or a part of role that can be basically defining a particular hypothesis, and its conduct are basically termed as don't care conditions, right? A third type of specific condition that can be prominently represented using a version space graph is a null value. So with the help of null value, we can basically specify some sort of values that cannot be evaluated for a particular time, right? So these type of values are generally represented using a phi or just a blank space, right? So as far as this example is concerned, whenever we are representing these sort of values, sky condition, air, temperature, humidity, wind, and water forecast, so we are basically utilizing the prominent values with some specific values. Like there are three prominent values in this example: sunny, strong, and same, right? But on the other hand, we are basically taking some don't care values also. Like we are taking don't care condition for air temperature. We are taking don't care for wind. We are taking don't care condition for particularly water, right? And we are basically specifying some of the conditions as the null values. Means they have a very limited role, or they at all not have any kind of significance in particularly deciding on the concept and the training concept values. So these are specified with the help of null values, right? So while plotting version space graph, we will be utilizing three types of values: specific, don't care, and null values. Now, the protocol concept learning task specifies a particular machine learning task or machine learning algorithm into three types of approach. First is the task, second is the experience, and third is the performance measure. In task, what we have basically, we have a target function. We use to perform the utilization of this target function to decide on a hypothesis, whether a hypothesis resulting in a positive frame set or it's providing some sort of negative training set, right? Target function is always a Boolean one. So we have for a particular task, when we are basically going to plot a machine learning algorithm it's basically a concept learning problem, then we define the target function. Target function will always represent a Boolean value. Either it will be a 0 value or it will be a 1 value. Now, what target function basically works on some sort of experiences that is basically indulged with some previous type of data sets, some previous types of values that can be specified, that can be particularly specified to it. So we are having a prototypical concept learning task like a hypothesis H can be represented, as I said in the previous slide, it can be represented in three types of values: uh, a don't care value, a specific value, and a null value, right? Now, what actually a performance measure is that whenever we are training some sort of algorithm, then when we are basically applying it to some practical type of problems, some real type of problems, then how it is basically performing, right? About the values it basically indulge in and about the results it's providing. So that will be making the performance measure P. We represent it with the help of a particular value that we are representing it with a P value. So there may exist several hypotheses that are basically best fitting the examples, right? Means we have to find the optimized level of solutions for a particular task, and these optimal level of solutions are basically representing the performance measure P associated with a particular machine learning algorithm, right? Now, what actually is inductive learning hypothesis, and what is the advantages of using inductive learning hypothesis over the concept learning task? So any hypothesis that is found to be an approximate to the target function well over a sufficient larger number of training examples will also be approximate to the target function well over other unobserved examples, right? So inductive hypothesis is just a specification about the concept learning task, that how well we are basically judging the performance of a particular machine learning algorithm based on some hypothesis plottings. Now, the very important thing is that what kind of approaches a learning algorithm basically utilizes, right? So learning algorithm basically utilizes a technique that is called a brute force searching, and on the basis of brute force searching, we are having different instances, right? And for these syntactically distance hypothesis, we have to provide some sort of results. We have to classify these results, whether they are some specific data is sufficiently large to classify a problem, or we need to impart some sort of very specialized type of methods on the basis of which we can basically classify whether a training set is a positive one or a training set is a negative one, right? So we are using a different technique. We are using various procedures. We are using, like in this case, we are using two types of approaches. One is based on ordering of hypothesis, right? And the second one will be finding the possible hypothesis utilizing the concept learning task. Now, the which hypothesis basically fit well will be the finally prominent answer for it. Ordering of hypothesis is basically instance based. Whatever we are having are instances, and on the basis of these instances, what concept learning tasks we are basically yielding from them will be providing some sort of hypothesis, right? So the hypothesis creation is based on some sort of algorithmic instance values, either a specific, don't care, or a null value, right? So with these values, like in the case, we are having two set of hypotheses. First is x1 and second is x2, right? So we will be evaluating on these type of hypotheses x1 and x2, and on the basis of this, we are basically creating two or three hypothesis values like h1, h2, and h3, right? And on the basis of this, we will be determining which of the hypotheses is more specific to the requirements is illustrated with the concept learning algorithm, right? So like we have plotted the instances for that particular example or approach into three phases: h1, h2, and h3. We will be evaluating those hypotheses on the basis of two types of algorithms. These are very significant algorithms, significant machine learning algorithms, and they have utilization based on version space graphs, right? So version space graphs are sophisticated graphs that are always used for finding a particular concept learning solution yielding any particular task and its performance measurements, right? So in FindS algorithm, what actually is, we are finding a hypothesis, right? We are finding the concept trainings and the training functions of that particular hypothesis. That is yielding two types of training examples. First training examples, we are getting a positive number. In the second training example, we are getting just a negative cycle, negative number, right? So whenever we are initializing a hypothesis, right, whatever be the result, we are basically yielding some positive training sets, we are yielding some negative training sets. But as we know that since memory is very limited, the major problem in implementing machine learning or the limitations of machine learning algorithms are that we are very specific, we are very limited in memory, we are very limited in, if we are basically deriving more and more memory, we are limited in the atomic latency of processors. Again, that is the hidden layers. So hidden layer approach, basically what we use, the hidden layers we are going to use will be very limited in approach, right? So the thing is that whenever we are having a lot of negative training examples, then they will be creating some sort of complexities in the machine learning algorithms. So our prime concern in the finders algorithm is to just ignore the negative training examples and just focus on the positive training examples, right? As positive training example will be yielding to some better performance of the algorithm. So negative training examples will be of no use, right? How we can basically remove these type of algorithms, these types of problems, negative training sets. It is basically governed with an algorithm that is called find S algorithm, right? So in find S algorithm, what we are doing, let's say we are having four type of hypotheses. First is X1, X2, X3, and X4, right? X1 and X2 are positive hypotheses, so we have grouped them together as you can see in the slides. X1 and X2 are basically part of a particular group, right? So they can be combined together. But as far as X4 is concerned, X4 although yielding a positive value, but it's not a part of that circle, right? So we have basically isolated X4, but it is being encircled in the positive domain. But as far as X3 is concerned, so X3 is basically yielding some sort of negative training example. So X3 is eliminated. X3 is eliminated from the positive sides, from the positive circle domain, but it is not excluded from the system. From the machine learning system, it is not excluded, it is just ignored, right? So we are ignoring X3 because X3 is a group of hypothesis type of training sets that is yielding some negative results, right? So the prime focus, our prime focus will be limited on accessing and analyzing three hypotheses that are X1, X2, and X4, right? And we will be simply ignoring the X3 value because X3 value is basically negative time, right? So this is the find S algorithm. So that's X1. X1 is yielding a plus, right? X2 is yielding a plus, and they are same because in both X1 and X2 the prime allocated value is first one, that is sunny, right? But as far as X3 is concerned, it's been changed, means we are getting a negative result. So this type of machine learning algorithm basically ignore the negative cycles, right? We are basically just making them isolated, right? So that processor can be protected from the overburdening of processing these types of data sets, right? X4 is again a positive, but since there are some values, there are very value change, like you can see from X1 and X2, we have a forecast same, right? But in X4, the forecast has been changed, means the forecast was of rainy day, but it's somehow, being converted to some sunny days, right? So whatever be the condition, we are getting the result as positive, but X1 and X2 are entirely different from the procedural level approach of X4, right? So X4 will be a part of it, but it will be in an outer domain, right? So these type of things we are basically doing. Problems in find S algorithm. Find S algorithm, although are a very good type of algorithm, but they cannot prevent the overburden of protecting or restoring negative training example, as negative training example will be stored in it, right? We are although we are isolating them, right, but we are basically allocating some memory space to them. We are not basically removing them, right? So memory is always occupied in find S algorithm. So that are the basic problems. Second one is that whenever training sets we are faulty, training data basically we are getting is in faulty data. So in this scenario, find S machine learning algorithm doesn't work well. Consistent hypothesis and version space graph are very prime requirements of the concern time, because version space, whenever we are plotting a version space graph for any kind of algorithm, be it find S algorithm or be it candidate elimination algorithm that we'll be discussing in the later half of the slides. So consistency is very important. Consistency is always required in an algorithm. List and eliminate algorithm is the second part of machine learning algorithm, is specifically designed for a concept learning task. In version space graph, we are having a particular list of hypotheses. All the hypotheses will be covered, whether they are reflecting some negative training sets, negative examples they are reflecting, or they are reflecting some positive training examples, but we have to include them all in the version space graph. So these are the hypotheses that we are discussing, although X3 is a negative, right? But we have to include in it. So this is the version space graph. This is a very, very important method that is being used nowadays. Decision trees were prominently used in way back in 1980s, 1990s, but in the current scenario, all the machine learning algorithms and all the programming algorithms like PyTorch and all the programming packages, they have a design and development approach. So these design and development approach are basically yielded with the help of version space graphs. So these are the version space graph of our problem that we have discussed in the just previous slides. So how to represent the version spaces? Version spaces basically represent three types of values, as I told earlier. First is a specific value, second is a null condition, right? And third is a don't care condition. We have a general boundary for them where vertices are basically deployed. Vertices are basically represented using some specified set of general boundaries known as edges, right? And there are some specific values in which we are basically representing some specific type of a particular attribute like a sunny, together rainy. These are particular attributes we are have to plot some specific type of boundaries to represent such type of particular attributes. So this is the theorem, although it seems to be very complex to you, but this is the theorem with the help of which we are basically plotting the version space graph over a particular hypothesis H consisting some data sets, right? D. So we have to plot all the negative and positive training examples that are we basically utilizing with the help of TE and TES that are training examples. So training examples are basically plotted with the help of graphs. So we have taken some sort of values for their representation as GH and S, right? Now, the very important, the second algorithm that we are going to discuss is candidate elimination algorithm, and what are the candidate elimination algorithmic parameters that we should have to care about. So let's G and S are some of the maximally general hypotheses in H. H is the complete hypothesis. We have some specific hypothesis also that is part of it. We are representing it with the help of S, right? Now, if D is a positive, we have to basically in candidate elimination algorithm, what different we are basically observing is that in finders algorithm, our search was limited to confined to tracing out the negative cycles, negative training examples, right? In this, we basically trace the negative training sets. We just make them isolated. We apply some sort of operations on them, but actually the problem was that they were consistently occupying the memory conditions, right? And as I told earlier, the biggest limitation is that we are limited with memory. And if we are providing a bunch of memory, abundance of memory, then we have to basically provide a very high atomic latency systems, high atomic latency processors that will be, making the overheads to run more in machine learning algorithmic implementation, right? So in candidate elimination algorithm, what we do is we basically judge the hypothesis general to a specific order. We start removing small s, that right means the negative training sets from the capital sets. We continue this process for minimal generalizations and up to which we basically yield some more generalized results. We keep on doing this process for every s value that we are getting in a hypothesis. We keep on doing this, and there comes a state which is an error-free state in which we have basically just eliminated all the negative training sets from the entire, right? So there comes a condition in which we basically have removed all the training sets that were apart once upon that were a part of that particular training set, but now they are, since they are reflecting some negative training values, so they are just removed on, right? So here you can see that S1 and G1, these are some values that we are having, and we have basically deployed the algorithm in an approach that they are removing the negative training sets, right? So these are some of the positive training sets that we have just analyzed. Moving on, next we have, right? So this is the condition, means we are moving from a generalized hypothesis to some specific type of hypothesis, and we are just plotting the version space graph for the candidate elimination algorithms. So there is a slight change in the version space graph as far as version space graph is concerned of finders algorithm, and version space graph of candidate elimination algorithm is termed. We are just marching from some specific to generalized sense of hypothesis, right? So moving on, next we have convergence of algorithms. So if there is no errors in that, means we are getting some containing some single H values, or the training set that we have deployed, the training example that we are using are basically more positive as compared to finders algorithm. Means the consistency, as far as consistency is concerned in the training sets, data training sets, we are getting some more consistent results whenever we are using the convergence of particular candidate elimination approach. This is another example that I have just taken for a problem, right? As I have discussed the sports example in the previous slides, so this is another example, and we have to apply some sort of procedures to find out, to trace out some sort of negative examples from it, and to sort out some positive examples from it, right? So this is the same scenario, this is the same condition, that we have to trace some examples over it. We have to frame two types of algorithms with these values, finder's algorithm and the candidate elimination algorithms, right? Now, whenever we are plotting a version space graph, the most important thing that we have to take care about is the consistency, right? Whenever we are plotting a version space graph, it should not be like that we have a lot of negative training examples, or we have some errors in secondary data collections or primary data collections yielding some bad results, right? So we must be very much consistent whenever we are plotting in choosing the algorithm. We should be very specific that these type of training sets have more negative examples, then we should move towards the candidate elimination algorithm. And if they are predominantly less, negative training sets are predominantly less in the concept learning task, then we can utilize the concept of finder's algorithm, right? So that we have to take care of it. So classifying new cases is almost similar. When we are having a value, then we have to classify the values into three conditions, that is sunny, okay, in this case, and rainy in this case, right? So these are two prominent values that are deciding whether a training example set is yielding to some negative type of training or a positive type of training, right? Effect of incomplete hypothesis space is very much negative effect they are having, because whenever a particular training space is not provided with particular genuine set of hypothesis data values, then it may result uh, in particularly negative training sets, right? So it will be affecting, the first thing is that it will be affecting the consistency. Second will be, if we are having a more number of training sets that are being negative, then particular result that will be provided will be unethical, right? So that should be taken care of. Incomplete hypothesis is always very a type of hypothesis that we cannot generalize with these specific values, right? So incomplete hypothesis spaces are a very abundant problems that a particular machine learning algorithm, as far as concept learning task is concerned, is faced. So unbiased learners and inductive bias are very important things. We have to utilize a value, like we can plot the Boolean functions with the help of these unbiased learning tasks. Means we have to apply the training examples so that there is no limitation on representation of hypothesis, right? There can be, we can apply disjunctions, we can apply the negations, we can apply some sort of predicate logics to derive on a particular result. Means to find out whether they are yielding some negatives or a positive hypothesis type of results. So unbiasing is placing constraints on representation of hypotheses, limiting connectivities to conjunctions, generalization hypothesis, introducing biases that depends on hypothesis representation, right? And needing some sort of formal definition of inductive biases of particular learning algorithms. So inductive systems and equivalent deductive systems are very basically the important parameters which can be utilized in order to basically define on a problem of uh, particular hypothesis testing and to deriving some sort of concept learning task. So these are very important procedures that we should take care of them. Root learners and version space candidate elimination algorithms that can be represented with the help of a particular target function. Okay, these are represented with a particular C value over a particular hypothesis. And we have, when we are basically have to find the finder's algorithm, then we are basically moving from generalized to some specified type of problems, right? So in the last, we are having a computational complexity of version space graph, that why version space graphs are better. So they provide some conjunctive features. They provide some expressive language to basically plot our algorithmic approach, whether we have to go for, with the finder's algorithmic approach, or we have to just switch to candidate elimination algorithms. So these are the basically two tasks, right? So these are exponential size of G that we have to take care of. There's a last summary. Concept learning search through H, general to specific ordering, version space candidate elimination algorithms. We are having inductive leaves where they are possible or not possible. So the biggest problem is inability to handle data, right? Which can basically provide some sort of errors, or which can overcome with procedures for learning decision trees, right? So that was all about concept learning tasks. I hope you all have enjoyed it. If you are having any type of suggestions or any kind of questions or queries, then you can put up in the dialog box below, right? Okay, thank you. Have a good day. Thank you so much.